and I begin reference 10, an introduction to topological groups, written by S.P. Bach. Okay, and in the following we see some concept from other books. For these topics, topological groups, we use reference number 10. Okay, an introduction to topological groups. And this is this book. That we can begin the study of this book in this session. Okay. This book started by the definition of topology. Okay. Dear students, do you have any questions for this course? If you don't have any question, let me begin the concept of this session. Do you have any question? This is the definition of topology. Let X be a set. A topology on X subset of X that satisfy the following three requirements, three conditions. 1. The empty set and whole of X must belong to 2. Please note that T is a collection of subsets of X. We know that empty set and X are subsets of X. Now, if tau is a topology, empty set and X must belong to tau. Given any family of element in tau, the union of this family must belong to tau, or tau must be closed under arbitrary union. Closure under arbitrary union. The union of any element of tau must belong to tau. And 3, given two elements in tau, its intersection must belong to tau. Closure under finite intersection. I write these three conditions again for you by another words. Let X be a set and tau be a subset of P of X. P of X is the set of all subsets of X. This is the set of all subsets of X. Then tau is a topology on X whenever we have these three conditions. Empty set and X belong to tau. For any family in tau, its union belong to tau. I is RB Okay, for any family in tau, its union belong to tau. Or equivalently, if for any alpha, a alpha is a subset of X, then the union of this A alpha be a subset of X, or equivalently this union be an element in P of X. These two are equivalent. This union is a subset of X, or this union is an element in P of X, because P of X is the set of all subsets of X. Okay, so that this is the condition 2. For any family in tau, the union of A alpha belong to tau. And 3, for any two element in tau, such as A1 and A2, its intersection A1 intersect A2 belong to tau. Okay, it is trivial that this condition equivalent to condition condition 3, equivalent to this. For any finite element in tau, the intersection of I from 1 up to the n, okay, this belong to tau. These two conditions are equivalent. If any two elements of tau have this property, equivalent for any finite element in tau, its intersection belong to tau. And it is very trivial that these two are equivalent, because, for example, let me write this for you in another okay. For example, if we consider okay, n family, a finite family, for example, n element into a1 an, okay, the intersection of I from 1 to n equivalent to intersection of I from 1 to n minus 1, then intersect by an. Now we can use induction, okay, by induction. See, this must be belonging to tau by the induction assumption, and this is an element in tau, then this must be belonging to tau, okay. So that this is very trivial that these two are equivalent. And for this reason we say closure under finite intersection, not two element. Okay, so that a subset of P of X is a topology if we have these three conditions, or we have these three conditions: empty set and X belong to tau. For any family in tau, its union belong to tau. This union is arbitrary, not finite. Okay, and 3, for any two element in tau, such as A1 and A2, A1 intersection by A2 belong to tau. Now we take some example. As the first example, let X be this set A, B, C, and we consider tau equal to this family of subsets of X: empty set A, B and C, and whole of X. Please note that tau satisfies the properties of topology. For example, we see that empty set and X belong to tau, and the union of all elements in tau belong to tau 2. For example, if we consider the union of empty set and this equal to this set, or the union of these two sets equal to X, the union of these two equal to X, and other union of element in tau, and also the intersection of any two elements belong to tau. For example, intersection of these two equal to empty set, intersection of these two equal to empty set, intersection of these two equal to B and C. Please note that in the definition of topology, if tau be finite, such as this example, this arbitrary index equal to finite, because we have finite element in tau. Okay, so that any subset of tau is finite. Okay, and as the second example, we see that for any set X, for any set, okay, if we consider P of X, tau equal to the whole of subsets of X, the set of all subsets of X. This is a topology too, so that P of X or tau equal to the set of all subset of X. Okay, mention that A belong to P of X equal to A is a subset of X. Okay, it is very trivial that this is a topology. For example, empty set and X are in P of X. Empty set and X are subset of X. And for any family of subsets in tau, its union belong to tau, okay? If we consider any family in tau equal to P of X, okay? So that for any alpha, a alpha is a subset of X, and so that its union is a subset of X, okay? And this is equal to the union of this family is an element of P of X. Is an element of P of X. Okay. Okay. It's clear that this union is a subset of X, so that this union is an element of P of X. And we see this example in example 2.2. For any set X, there are two topologies arise commonly, the discrete and non-indiscrete topology. One is P of X. P of X is a topology and it is called the discrete topology, okay? P of X is the notion for the power set of X, or the set of all subsets of X. And another example is empty and X only. This is a topology too that is called indiscrete topology, okay? It is very clear that any topology on X must be contain empty set and X. This is the first condition of topology. So that this is the smallest topology on X. And clearly this is the greatest or largest topology on X. Largest topology on X. Okay? Sorry, I have a problem in or both. Okay. And it is very trivial that these two satisfy the condition 2 and 3 for topology, okay? Any union of these two sets is one of these two sets, and any intersection of element of 2 must be belong to 2. For example, the intersection of empty set and x equal to empty set. The intersection of x and x equal to x, and other cases. And it is very important that any element of 2 is called an open set. Please note that if 2 is a topology on X, then members of a topology are called open set. Any member of this 2 is called an open set with respect to 2. Any element is called an open set. Okay. Okay. So that this union is an element of P of X. Okay. I alpha meta belong to I. Okay. It is very clear that any topology belong between these two topology. These two are very extreme. Indiscrete topology and discrete topology. Okay. So this is the smallest topology on X, and this is the greatest topology on X. Note that any topology tau is closed under finite intersection, that I mentioned that for you. This intersection equal to this intersection. Okay. So that these two are equivalent. These two are equal. This is very trivial that this condition implies this condition. Okay. And we see the opposite direction by this method. And we have this definition. Let X be a set and let tau 1 and tau 2 be topologies on X. If tau 1 be a subset of tau 2, then tau 1 is closer than tau 2. And if we have this inclusion, then we say tau 1 is thinner than tau 2. Okay. Tau 1 is thinner because if, for example, tau 1 be a subset of tau 2 or tau 2 be a subset of tau 1, we have probably finer or smallest sets in 2 1. We say that 2 1 is finer than 2 2. Okay. Now we have a very important example. The element of Euclidean topology on R to the power of n. R is the real numbers, okay, are unions of open balls in this set. This topology denoted by this a special case that we will make constant reference to is R itself. Here open sets are unions of open intervals, so that in this set we consider this topology. If we consider x equal to real numbers, tau equal to the set of all unions of open intervals. AI and BI is an open interval, okay, such as 1 2, okay, 3 5, and other open intervals. If we consider the set of all unions of open intervals, this tau is a topology. And the proof of this is very easy. I write this for you. It is very clear that empty set is an element of tau and R belong to tau, because we can write empty set equal to this union, the union of intervals that this alpha belong to empty set, and whole of R equal to the union of this intervals minus n and n, minus 1 1, union by minus 2 2, minus 3 3. The union of all of these intervals equal to whole of R. So that R is a union of open intervals. So that R must be belong to this tau. Tau equal to the set of all unions of open intervals. Okay. The set of all union of open intervals. And as a generalization of this example, if we consider also we have other conditions for topology. For example, if we consider two elements in tau such as A alpha and A beta. A alpha, for example, is this union of open intervals, and A beta equal to this union of open intervals. So that A alpha intersect by A beta equal to this intersection by this. And I write these two, and the intersection of these two sets equal to this union. It is very clear that this union belongs to tau, because this intersection is an open interval or empty set. If we omit the empty sets, we see a union of open intervals. and so this must be belong to 2. Dear students, do you have my voice? Okay, thank you. So that we have this three conditions. Please note that x equal to real numbers and 2 equal to the set of all subset of R by this form, union of A alpha and B alpha, such that alpha belong to I for each alpha, A alpha and B alpha is an open interval. Okay, I say that it is very clear that empty set and R belong to 2 as the first condition. Okay, and if we consider 2 elements such as A and B in 2, then there exist 2 families such as these two, A alpha, B alpha, alpha belonging to I, and A beta, B beta, beta belonging to J, of open intervals such that A equal to the union of this A alpha, B alpha, and B equal to this union A beta, B beta, beta belong to J, because the element of 2 must have this form. Okay, so that this intersection equal to this intersection A alpha B alpha, alpha belong to I, then intersection by this union A beta, B beta, beta belong to J. Okay, this equal to A and this equal to B, and this is equal to the union A alpha belong to I, beta belong to J, then A alpha, B alpha intersect by A beta, B beta, and this is an interval or empty set, so that this is an union of open intervals, so that this must be belong to 2 again. Okay, for any 2 element of 2, such as this and this, its intersection must be belong to 2, and we write this for you in this place. Okay, and finally, for any family in 2, we see that if we consider this family in 2, for each alpha, A alpha is an element of 2, so that A alpha must be written as a union of open intervals. Okay, A alpha can be write as an union of open intervals, such as this, so that the union of A alpha equal to the union of this set, because A alpha, okay, because this A alpha equal to this, A alpha equal to this, and this is a union of open intervals, so that this must belong to 2. This must be belong to 2. This must be belong to 2. Okay, this A alpha equal to this by this equality, so that the union of A alpha equal to this union, and this union is an element of 2. Okay, so that this the Euclidean topology on R to the power of n is a very important topology. And we have this definition: a set X together with a topology 2 on X form a topological space. This denoted by the pair X and 2. So that if 2 be a topology on X, we say this order pair by a topological space. This is a topological space. And also we have this definition that X and 2 be a topological space and X belong to X, except n as a subset of X is a neighborhood of X if there exists some element in 2 with this property: X belong to U and U be a subset of n, so that n is called a neighborhood of X if we have an open subset of X, such as U, such that X lie between X and n. X belong to U and U be a subset of n. In other words, n is a set that contains an open set containing X. An open set containing X. And the set of all neighborhoods of an element X will be denoted by nx. Please note that this is the definition of topological space. X and 2 is called topological space, and this is Euclidean topology on R, the set of all subsets of R such that A can be written as a union of open intervals. Okay, I write the proof of this again for you. I send this file for you together with your source book. Please note that for real line, interval is this subset of R. In the case n equal to 2 in plan, this product equal to this square, and in n equal to 3, this product equal to this cube. And we know that in Euclidean topology on R to the power of n, we have 2 equal to the union of these products. Okay, all of these are open intervals in R, and we consider the multiplication of these open intervals n times, okay, because this must be a subset of R to the power of n. As some example, we see that this is an open set because minus infinity and the root of 2 equal to this union of open intervals. This union of open intervals, okay? These 2 radical 2 and other intervals, the union of all of these equal to this, okay? And from 1 up to the infinity. And we know that all of these are open intervals, and this union must belong to 2. Because we know that 2 is a the set of all subsets of R with this property, all union of open intervals, okay, or this, the set of all subsets of R that A can be written as a union of open intervals, okay. And this union is an open set too, because this is an union of open sets. For more easier, we can consider, for example, this union is an open set, okay, this is an open set. One, 2 is an open set, because it is a union of open intervals. One open interval, okay, and other open interval is an open set. Any element of a topology is called an open set. Is called an open set. And also we have the definition of neighborhood. For example, if we consider okay, okay, and we can consider in Euclidean topology this is a neighborhood of, for example, 2, because a neighborhood is a subset of X such that there exists an open subset containing X, okay? Okay. Of 2, for example, because we can consider 2 as an element in 1, 3, and this is a subset of this set, so that this is a neighborhood. There exists an open set, okay? This is open set, and this is contained 2, and this is a subset of or n. This is or n, for example, in this definition, okay? And U is or open set. And we have this definition, let X and tau be a topological space. We say that a subset F of X is closed when the complement of F with respect to X belong to tau, so that So that if X and 2 is a topological space, and F be a subset of X, F is closed if and only if its complement is open, or equivalently F is closed if and only if X minus F belong to 2, because we know that these two are equivalent. A subset of X belong to 2 if and only if it is an open set. Okay? For example, if we consider minus infinity and radical 2, we see that this is an open set. Is open in Euclidean topology, okay? Because this can be written as union, okay? So that this is a closed subset of real numbers. Is closed because its complement radical to infinity complement, or r minus radical to infinity, equal to this open set. This is an open set, so that its complement is closed. It is very important that F is closed if and only if the complement of F is closed if and only if the complement of F is open. And we know that if we consider this as our set X, and if we consider this as our its subset F, for example, this is X minus F, okay? The complement of F. The complement of F. The set of all elements in X that is not belong to F. Okay. Dear students, do you have any questions? Continue in the next session, okay? We will continue in the next session. Okay? Thank you very much. Thank you for your attention and goodbye.